For the introduction. The title of my talk is Architecting Query Compilers for Diverse Workloads. Parts of this work was in collaboration with Grigory Issertel, Shilian Wu, and TR Krumpf. So database management systems has been around for decades with tons of work optimizing every corner of the query engine. Recently, main memory platforms has eliminated the I/O cost, and the workloads have become CPU bound. So compiling queries into low-level code has become feasible. I would like to point out that there has been several works on compiling parts of the data management or the full data management. However, none of these work have addressed specialized workloads like spatials and graph. And since I'm speaking in a PL venue, I would like to demonstrate the performance of a relational workload. So I picked the simplest query from the standard TPC-H benchmark. Query 6 essentially performs a single aggregate operation on a single table. And the C code below shows the same query in C. And I want to point out also that the data size is 7.3 gigabyte in this demo. So if we take a disk-based database management system, it takes 2 minutes and 42 seconds for data loading and about 9 seconds for runtime. What else out there? Spark is a main memory management system. So it takes 17.7 seconds if I'm to run this query directly from a CSV file, or I can persist the data, and it takes 1 minute and 42 seconds and roughly 1 second for runtime. But what really we hope for is the performance of handwritten code. So in this case, it takes 8 seconds for data loading and 230 milliseconds for runtime. Some motivation on spatial workloads. So with these mobiles and Internet of Things applications, so we have tons of spatial data, and there are interesting queries, whether it's proximity and nearest neighbors, that also can benefit from this type of acceleration. And I want to point out that these spatial query engines are implemented either as extension to a relational database management system or a MapReduce system like Spark. Some motivation on the graph side. So graphs are everywhere, whether it's a social network, a road network, and there are several query workloads like triangle count, page ranks that keep on showing up. And these workloads need to be run as fast as possible on very large data. So now I'm done from the motivation. For the rest of this short talk, I will focus on the key idea of architecting a query compiler for diverse workload. So a query engine works almost like a query compiler, except it misses the final code generation step. So there's a front end, parser, optimizer, and a back end, but we don't have a code generation part. So the key architectural question is how to get from a query plan to an executable code. And if we look at the current work, it seems we're stuck in these two extremes. So the low-level approach, which is implement the whole query engine using precompiled C++ and generate LLVM code, which works great, gives excellent performance, but this is very hard to implement. And on the other side, we have a high-level approach which built the query engine or query compiler in high level and use multiple compiler passes to convert this high-level processing code that consists of so much data structures to a low-level code. So this is the two extremes that we have. And in both cases, there's a significant development effort than writing a simple query compiler. So what we really need to do is to find a way to be able to use the high-level approach, but using a single compilation pass. So this, of course, will lead us to the Futamura projections. And the first Futamura projection that links the interpreters and compilers through specialization. So the key insights of the first Futamura projection is compilation can be profitably understood as a specialization of an interpreter without explicit reference to hardware or code generation mechanism. And Futamura projections were very well perceived in academic circles, but they had less practical success due to the difficulty of the automatic partial evaluation. So what we did in our system, which is called LB2, we found a practical way to realize the first Futamura projection with help from the programmer. So in this visualization, in figure A, I show a query interpreter, which evaluates an SQL query and produce the result, and this is very slow. And if we take the first Futamura projection, it says if we have this mix, then we can evaluate this SQL, then we can evaluate an SQL query with respect to this SQL query engine, which is essentially an interpreter, and produce a fast target. So, but this mix doesn't exist, so what we can do is stage this query interpreter with help from the user and get the same result. So programmatic specialization or guided partial evaluation, suppose that like a very small toy example here, if we have the power function, which takes 2 arguments, and we happen to know the exponent, then we can write a specialized residual function. And this can be done one way by defining a symbolic type, my int, that emit the desired specialized code as side effect at evaluation. And we did really the same inside the query engine, but instead of just using the printing, we used the lightweight modular staging for code generation. And for the short time, I want to show a high level of this query engine. So it compiles relational, spatial, and graph query. So the core of this query engine is the data structures. So the efficient generation of hash maps, spatial indexing, and adjacency structures that give us good performance. And here's some, I picked some of the results. On the relational side, we ran the full TPC-H benchmark. We compared with Hyper, DBLab, and Postgres, and I want to tell you that Hyper is the best low-level available query compiler, and LB2 is comparable to Hyper. And it also outperforms, of course, Postgres because it's a disk-based, and DBLab, which also the other system that uses the multiple passes. Also, we did some experiments on spatial data, and we compared with the existing system, which is Spark extensions, and we outperformed the existing systems. And finally, we compared with some of low-level graph engines. We compared with triangle count and PageRank, and we were either on the same ballpark or outperformed these systems. That was my talk. Thank you.
So we have time for a couple of questions for Ruby. So one thing I wondered is, do you have to provide any annotations as the author of the queries that you're writing, or even if you did, would that be beneficial?
So like the SQL side, we don't do any annotation. We annotate the engine code.
But if you provided some annotations, is there in the query, would you be able to specialize better in the engine?
You mean like some things for the optimizer or something for, well, I mean, as far as what we do here, like the engine is independent of the SQL query. So the SQL query gets mapped to some plan, and then this plan gets mapped to the engine code. So there isn't any annotation in the front end.
So you don't do any any code generation at query time?
So we get the query from the user. We just map it to the engine, and the engine is the specialized part, and then this is what gets executed. Yeah, thank you.
Any other questions? Okay, well, let's thank Ruby again. Our next